Triple integrals in rectangular coordinates. So we'll first evaluate a couple integrals that are already set up for us, which should be pretty easy overall. You're given this form, and the limits are 0 to 1, all three of them. Of course, we have the form dz, dy, dx. We're going to integrate z's and y's and x then. So first you get z, and z cubed over 3 basically comes because it's like x squared, y squared, is multiplied by z, because it's like a constant value. Z squared becomes z cubed over 3, z equals 1, z equals 0, and of course we're subtracting 0 from all this thing, so it's x squared plus y squared plus 1/3. Z cubed is 1, because 1 cubed is 1. Z is 1 here, so it just becomes x squared plus y. And that kind of similar trend happens onward, sort of. Simplifies down that after you integrate with respect to y and plug in the limits, you get x squared plus 2/3 dx. And you integrate that with respect to x, and you'll get 1/3 plus 2/3, which is equal to 2 over 3, which is equal to 1. So all you do is follow the steps to integrate. And that's why these are good to do 1 or 2 of these to make sure you can get the basic process before you start messing around with setting them up by hand. The whole integral. So this one's a little bit trickier. So we integrate z's and y's and x. Similar to double how you do either y's and x or the other way around. Basically you have to follow the order. So with respect to z, we have, so this whole thing just with respect to z, it's just like 1, so it's just z. That's square root of 9 minus x squared minus 0. Those are the limits here. So it's just square root of 9 minus x squared dy dx. So we integrate that with respect to y, and you can kind of just pull that out as a constant, and it's just y, where y equals square root of 9 minus x squared and y equals 0 to limits. And it's just going to be square root of 9 minus x squared, similar to the previous thing. And there's the product now of these two dx. So the square root cancels out and you get 9 minus x squared dx. Now we're integrating this with 0 to 3, so we get actual value here, but we'll get 9x minus x cubed divided by 3. That's what 9 minus x squared becomes. And then x equals 3, x equals 0 limits, and you evaluate, and you eventually become 18. Solution is 18 to this one. And the rest of the problems are finding the volume of the regions given. So we have like 5 problems where each of them is a different region. The book provides images, but we're going to try to avoid that for this, because on an exam, you're not going to always be given, if you're not given an image, which is common, you just have to figure out based on a few words. Like a word problem like this, a sentence or two. And you can generally don't need it though, the picture, because it's hard to sketch 3-dimensional structures. Unlike 2-dimensional, with double integrals, you can more easily sketch things out. Because it's x and y is pretty easy to sketch, but x, y, z, not too easy. Don't even get started on when we get into the next 2 sections, when it's a lot even harder to sketch out. Some of these regions. So we have the cylinder, z equals y squared. It's the region between the cylinder, z equals y squared, and the xy plane that is bounded by the planes x equals 0, x equals 1, y equals -1, y equals 1. This one is very self-explanatory. You already have your x and y limits given. And z is just 0 to y squared. You can tell because, it's going to be z equals 0 is going to be the bottom limit. Obviously because xy plane is between the cylinder and xy plane. XY plane is flat, is where z equals 0, pretty much in general, so. That's why 0 is the lower limit and y squared is the upper limit for z, and then x equals 0, x equals 1, and then y equals -1, y equals 1. And we're finding the volume, so it's dz, dy, dx, just alone. 1 dz, dy, dx, whichever way you want to spell. Same z. Dz, dy, dx. So, integrate. So it's z equals y squared, is what's plugged in, pretty much, and z equals 0. Of course, y squared minus 0 is just y squared. We have to integrate that with respect to y, so it's y cubed over 3, y equals 1, y equals negative 1. We eventually get 2/3 dx, and then that's 2/3 x, so x equals 1, x equals 0, so it's just 2/3. And volume equals 2/3. Now let's get a little bit trickier. The region in the first octant bounded by the coordinate planes. So we have coordinate planes, the plane y plus 2 equals 2, and the cylinder x equals 4 minus y squared, and it's in the first octant, we're told. So coordinate planes is x equals 0, y equals 0, c equals 0 as lower limits. X equals 4 minus y squared means that when y equals 0, x equals 4. That would be the upper limit for x. Y plus z equals 2 means that z equals 2 minus y. That'll be the upper limit of z. And y, we can solve x equals 4 minus y squared for y to get y equals square root of 4 minus x for the upper limit of y. We set this up 0 to 4 for x, 0 to square root of 4 minus x for y, and 0 to 2 minus y for z. You kind of want this order to make sense, so you eventually get an actual value. 0 to 4 I think can send up, but I think in this case especially, upper limits are all it really work. In most cases for rectangular coordinates, a lot of times your lower limits are going to be 0. The real trick is finding out what to do for your upper limits. Well, not. Yeah, so just to reiterate and make sure you understand how we got these upper limits, you can see we're in, but we have a cylinder in the plane, y plus z equals 2. Yeah, I'm pretty sure. I mean, you could technically do another orders, but point is we got x in terms of just numbers, pure numbers, so that's the last one we integrate. You want your last integrand to give you an actual number, so just values 0 and 4. Makes sense for that. It's at the very least what you'd want. You don't want any more variables when we're done integrating all 3 of these integrals. But then you eventually you integrate like before. It's pretty standard until we do the second one where we respect as y, because we have 2 minus y dy dx. We get 2y minus y squared over 2, and then we have to plug in y equals square root of 4 minus x and y equals 0. So it's still fairly standard, but I simplify it down to you have 2 square root of 4 minus x minus 4 minus x over 2. And I try to simplify it down. So 2 square root of 4 minus x minus 2 plus 1/2 x dx. Integrate that, respect x. And we have to do u substitution pretty much for this one, but 2 parts of it work out. So we do u substitution. And this is one of the times I'll just I substitute it back in at the end with x, because it's part of this bigger thing. That'll work out better that way. So you get negative 4/3 4 minus x raised to the 3f's power, because basically you let u equal 4 minus x and du equal negative 1 dx, so dx equals negative du. You plug these in, you get integral 2 square root of u minus, negative du. So it's negative 2 times the integral u to the 1/2. We write that as power du. And you integrate that, so you get u to the 3/2 divided by 3/2. So it's negative 2 times 2/3. And then u becomes 4 minus x, and that's raised to 3f's power. Basically. Another part's integrated normal. Negative 2 becomes negative 2x, and x 1/2 x becomes x squared over 4, because it's x squared over 2 times 1/2. Then we plug in the limits x equals 4 and x equals 0, simplify down, and we get 20/3. So a little bit extra simplification to get 20/3. Okay, this one is a doozy of a problem. It's really long because it's just one. So the tetrahedron in the first octant bounded by the coordinate planes and the plane passing through these 3 points. So we have to find an equation of a plane first. We're not given it like before. And the ones, most other ones have us given everything pretty much. We don't have to figure out a plane. So an earlier section from a while ago, we create our 2 vectors, PR and PQ and PR, by labeling PQR, these 3 points, PQ and R. We get our 2 vectors and we take the cross product to get the vector n, which is like normal vector. So it's cross product like before, it's not too hard to take this one, and we get 6i plus 3j plus 2k is a vector here, and we just use the point P. We pick any one of the points and this vector to create a formula. So 6 times x minus 1, and I color coded them. We're getting from, you simplify this down, eventually you get it in terms of z. Z equals 3 minus 3x minus 3 halves y. You want it in terms of z, because the plane is generally given like that for these problems. Because a lot of times you want to integrate with z first as well. You know that, but that's just general. So coordinate planes means x equals 0, y equals 0, and z equals 0 are lower limits. So z equals 3 minus 3x minus 3 halves y is upper limit, as we showed before, was all that work to get a plane for it. If z equals 0, that means 0 equals 3 minus 3x minus 3 halves y, which you solve for y, eventually you get 2/3, you get 2 minus 2x if you follow this work. That's the upper limit, y limit. Then y equals 0, we just solve for x now. 0 equals 2 minus 2x, 2x equals 2, that means x equals 1 is the upper limit for x. So you get 0, 1, 0, 2 minus 2x, 0, 0 to 3 minus 3x minus 3 halves y, dz, dy, dx. And we start solving for this 3 minus 3x minus 3 halves y, you integrate with respect to y. Usually with these ones, these volume with rectangular in particular, it's very quick. You just integrate step without 2, it could take some time. I do some simplification work to make it so our final integral won't be too messy, but it still will be a little bit. Because 3 minus 3x minus 3 halves y with respect to y, it's 3y minus 3xy minus 3 halves times y squared over 2. Let me simplify this out. Oh no, because of the limits. Y equals 2 minus 2x, that's when we left simplify. Yeah, 2 minus 2x squared is also annoying. At least the lower limit, it's just 0, 0, 0. 0 minus 0 minus 0. The subtraction of that. Because of all the multiplication. 0 multiplied by anything is 0, 0 multiplied by 0, 0, yeah. So 2 minus 2x squared is equal to 4 minus 4x minus 4x plus 4x squared, so it's 4x squared minus 8x plus 4. That's what we get. So distribute. You continue simplifying down. Eventually you get the integral 0 to 1, 3x squared minus 6x plus 3 dx. And this one can be easily integrated. So you get volume equal to 1 when you actually do all the steps. All that work for just volume 1, but okay, 2 more of these now. The region common to the interiors of the cylinder is x squared plus y squared equals 1 and x squared plus z squared equals 1. This will be in all octants because there's no coordinate planes boundary, so we find volume of 1 octant only and then multiply that value by 8. Therefore our lower limits will be 0 because we're doing just one of the 8 octants. The 3-dimensional coordinate system. X squared plus z squared equals 1 means that z squared equals 1 minus x squared, so z equals 1 minus the square root of 1 minus x squared. You can do that for x squared plus y squared equals 1, same thing, you get y equals square root of 1 minus x squared. And if you set y equals 0, you can get x squared plus y squared equals 1 to be x squared equals 1, so that's x equals 1. So the volume is 8 times the integral, the triple integral here, so 8 times it. So we'll solve the triple integrals and we just have to take 8 times it to get it. And this integral takes not long to solve, as can be seen, it's solved on this page. Okay. So just to make recap, so 0 to 1 is x. 0 to square root of 1 minus x squared is y, and 0 to 1 square root of 1 minus x squared is z. Z dy dx. That's 1 octant volume. This thing's in 8 times. It will give you the full spectrum, but full volume. So we're just solving for 1/8 the volume is the main point, and we multiply by 8 to get it. Because of the 2 cylinders, that's how it works. So you get z. You just keep on going in, and it's similar to one of the, it's like the second one we solved, kind of where you get, things can't, things simplify down naturally. And you eventually get 2 thirds, then you multiply that by 8, so it's 8 times 2 thirds is 16 thirds. That's the volume. The last one, the region in the first octant bounded by the coordinate planes, the plane x plus y equals 4, and the cylinder y squared plus 4z squared equals 16. X plus y equals 4 implies that x equals 4 minus y. Yeah, I think, because y is common, you want sort of y to be like your last thing to integrate, I think, in this case. Sometimes you can do it like that. Please. Y squared plus 4z squared equals 16 means that eventually you simplify down to z equals square root of 16 minus y squared divided by 2. And if z equals 0, you have y squared plus 0 equals 16. So y squared equals 16, y equals square root of 16 equals 4. So we integrate 0 to 4 for dy. Will correspond 0 to that's z equals that's then x equals 0 to x equals 4 minus y. And this one takes a little bit of work to solve. So the first step, you just get 4 minus y dz to get y, dz to y. Your first integration step, so not too bad. Now integrating to suspect the z, it's just 4 minus y times whatever the integrand gives you for just z. Oh, and it's low limits of 0, so it seems pretty simple. So you get 4 minus y multiplied by square root of 16 minus y, square root of 16 minus y squared divided by 2. And you can tell this is not going to get good. We only have to do one more integral. How bad can it get? Well, it gets a little bit annoying. More tedious than anything. So yeah, we can split this up into 2 separate integrals to make our job a little bit easier. Simplify it even further, so it's doing these steps because I distribute them in. We get 2 integral 0 to 4 square root of 60 minus y squared dy minus 1/2 integral 0 to 4 y square root of 60 minus y squared dy. So now let's go on to solving this. V equals 2 times 10 to, so basically we write it. So we, 2 different colors, red and brown. So 1/2 integral 0 to 4 y squared root of 60 minus y squared dy. This one is actually the easier one to do. Well, it was without copping out. Let's just say I did this one. The other one, the second one, I looked at a table of integrals, and you'll see. U equals 16 minus y squared, and then you keep on going. Du equals negative 2y. dy equals du over negative 2y. And you have u equals 16, u equals 0. I'm plugging in the 2 limits. So we have this situation, and the y's cancel out, so you just get in terms of u and du. So it's negative 1/2 u to 1/2 du. Can be integrated, and you eventually get 32 thirds. That's the easy part. This whole mess in red. So that gives you the right one. So we got the 1/2 integral this area. 32 thirds. So we subtract this from whatever we get from the first integral. So just the integral of 0 to 4 square root of 16 minus y squared dy. I wrote this in the form 4 squared minus y squared. This is the form a squared minus y squared, just to keep up. Or in general, you could say a squared minus x squared. So basically, I did that. So it's y. It's this time the variable y, but any variable we can use that to apply the formula. we can use a general formula from a table of integrals. Y halves square root of 4 squared minus y squared plus 4 squared over 2 sine inverse of y over 4, where a squared is 4 squared. A is 4. 4 squared, it's... And look in the back of the calc book, and you'll see a bunch of table of integrals in one of the appendix, glossary, whatever you want to call it. It's called. And normally you'd have to use trig substitution or something like it to be able to solve this, to get like a formula like this. I mean, I just thought, why not? Just take the easy way. Like, this is calculus 3. Calculus 2 is when you do trig substitution in general, in most places. And I don't think you'd be expected to be able to do this off the top of your head. So we'll just go with using a table integral so we can solve the end of this problem. But eventually you plug your values y equals 4, y equals 0 into this formula here, gone from that integral table. And eventually you get 4 pi. So this is equal to, this formula volume is 2 times 4 pi minus 32 thirds. So it's equal to 8 pi minus 32 thirds. Yep, 8 pi minus 32 thirds, and that's it for that section on rectangular coordinates, triple integrals and rectangular coordinates. Thank you for watching.